So here I will run an example stressing how you should implement the different stages of data mining. Therefore, I will use an example. The example is coming from Berkeley. So it's small data sets of 50 specimens. Each specimen is a flower, an iris, which is described with 5 data, 4 attributes describing the length and width of the petal and the sepal of the flower, and 1 characterization of the species of the flower. So there are 3 different species in our data sets: the Iris setosa, Iris virginica, and Iris versicolor. The objective of this example is to predict the species of the flower that you will study. So of course, in real life, when you are facing a flower, there are multiple aspects that will be used to classify the color of the petal, the place where you found the flower, and so on. But here the objective is only to use those 4 numerical attributes to predict the species. So I will use Jupyter Python to study this sample. You can find the file on Hippocampus, so you can rerun it on your own to see how it works. So here is the document. So the first things to do is import all the libraries that we will use and import data. So here you can see I will use NumPy to treat the data, PyLab to represent the data, Panda to store the data in a usable way, and also scikit-learn. But there are other libraries that could be used. So now that I import everything, I will be able to represent the data. So for this example, the data are clean. So I will not detail the cleaning aspect. You will do that on your own for the exercise you have to send me. But here, the data are clean. We can use it as they are. So I will store all the data in a Panda frame, which is easier to manipulate in Python. For instance, you can see easily how we will manage the characteristic using keys of the different characteristics. So we can count how many we have. For instance, here you can see that we have 50 specimens of each species. So here is the entry line you have to type to verify if there are problems in the data. So verify that no data is missing. And we can describe here using this functionality of Panda frame, what are the characteristics of the different data description. So then we can use the tools already embedded in Python to represent the data. So here I represented on a scatter plot the width of the petal in function of the length of the petal. You can see that they are quite well spread. You can also see that the petals are quite longer than the sepal are longer than the petals. So when you will be using distance, it might cause problem. So we will have to normalize those data. So we can represent the data as a whole, or also stress the information that we have on the spaces. So here we have the 3 different spaces represented. And as you can see, some spaces here, the red one is quite different for the other one, but here it's not so easy to differentiate the blue and the green spaces. So in addition to scatter plot, we can also use histogram to describe data. Here you have here petal width in function of sepal length, petal width or petal length. And here's the repartition of the value on an histogram. We can also use those kind of box plot to represent data. And here you can see that because the petal and the length and the width is so different, it's difficult to see what happened here for the setosa spaces. One interesting way of visualizing is using this parallel coordinate that enable to stress the repartition of the specimen and stress which characteristic enables to make a difference. And here you can see that if you have to use only one description value to sort the different flower, you should use petal length. This is the dimension that enables to discriminate the different species more easily. So if you have to use only one dimension, choose this one. But then we can choose to not use already existing dimension, but use principal components analysis to create new dimension to represent the data. So this dimension reduction is important if you have a lot of dimension and it's not so easy to represent in 2Ds. So what you will do, what does this principal component analysis is a projection of the n dimension specimen in a 2D plan. So here, using those already embedded functions, we construct 2 dimensions which have no real existence, but are a linear combination of the real description of the flowers. And it enables to represent the reality in 2Ds with the minimization of data loss. So this is how it works. It chooses a vector to project the 4D data into a 2D plan with a minimal loss of information of data. If you want to know how they are chosen or how they are constructed, here you can see how from the 4 real dimension, so width and length of petal and sepal, you can construct those PCA dimension. And here you can see that the first dimension enable to represent 92% of the information, and the rest come from the second dimension. So in the transformation from 4 to 2 dimensions, we only lost 2% of the information, which means that using those 2 PCA attributes, we can represent the real specimen into a new 2D plan without losing too much information. So this is a good way of representing data, because using this new PCA dimension, you will be able to represent everything in a 2D graph, which is much more easy for the human eyes. Then we want to classify our data. So we can classify data using Gaussian naive algorithm, which is already embedded. But therefore, we need to, since it uses distance, we need to normalize data. So here is the normalization of the data so that we have no problem using distance. So you have to start those process, which will be the same for every method. First you learn, and then you apply what you've learned on a test set. Therefore, you need to cut your population. Here we have 150 flowers, but we need to split this population in a learning set and a test set. The learning set will be used to build the model, and the test set to identify the performance of this model. Here you can see we use the learning step to set our model. So we use the feature describing the product and the label that we add, and then we can predict the values of our new classification. And then you can evaluate if the prediction you made is good or not, because we have the label for every flower. So for instance, the real species of the flower was here modeled as 0, but the prediction of the Gaussian Bayesian was 1, so the prediction was false. So the classification is wrong. But you shouldn't test on only one, so you will be able to calculate the accuracy for every specimen in the test data. And here you can see that we are available to predict the right classes of flower, the right species for 93% of the flower. So it's a good method, even if the first one was wrong. We can depict the confusion matrix. Here you can see we have no problem classifying Setosa, Virginicolor. Here we have only problem here when we misclassify for iris. So there are numerous key performance indicators that you can calculate and study. And you can do that multiple times by changing the learning set and the testing set to see if, depending on the choice of the repartition of those two sets, the results differ. So in mean evaluation, Gaussian naive Bayes enables us to have a 95% prediction accuracy, which is good. Then we can use another method to obtain the same classification, which is clustering. So here we know that we want to have 3 clusters, which will correspond to our 3 spaces. So we know how to set our parameter. Here we say that we want to have 3 parameters, 3 number of clusters. As you can see here, I'm not specifying the distance. And per default, in Python, the distance which will be used is a Euclidean one. If you want to choose another, it's possible. You have to specify here the distance you want to choose. So here is the cluster obtained using the 3 means algorithm. We can then compare the obtained classification with the real one. For instance, if you want to visualize, here you can see the real info and the predicted info. We can also represent it in a different way, like here. You can see here you have the right info, only one plot. Here you have errors. So you have to be careful on how to read this graph, because as you can see in Abscess, you have the label of the real cluster, which is 0, 1, and 2. So we lost the text info. We have real class 0, but you don't know if it is setosa or versicolor, so you have to dig later on. And the same for the predicted class. You have class 1, class 2, class 0, but you don't know which is which. So this is a good way of knowing if the errors are important or not, but you have to dig deeper to understand where they are. Another method that can be used is the agglomerative clustering. So again, this is a totally embedded method, which you have to use specifying the parameter, with kind of distance you're using. Here I'm specifying I want to use the Euclidean distance. I want to use the complete linkage, and then everything can be done smoothly. By using the embedded algorithm, you will obtain quite rapidly the information and plot it as a dendrogram. So here you can see how the different specimens will regroup to build those 3 clusters at the end. You can also use this dendrogram by specifying the color of the leaves and then represent the real data. So it's quite interesting to see it. Here you can see you have those flowers which are very similar, so they belong to quite early in the process to the same cluster. And here you can see that those flowers, blue or green, they are quite similar, and so maybe it's not possible to distinguish them only by using length and width of petal. Maybe if you could know the color of the petal, if you know where you pick those flowers, you will be able to sort them, but the data you have doesn't enable you to do this sorting. So this is also interesting, to be able to identify that information cannot be obtained from the existing data. This will give you hints of how to enrich the data you are storing to get the result you want. This is something that you will have to stress when you will study the car dataset and suggest which kind of other data might be used to make better prediction.